Good morning. So today's lecture, let's continue on AC circuits. Just a moment, I think I have a technical issues. Okay, so the AC circuit analysis, as we discussed before, the procedure first, we need to convert the circuit from time domain to phasor domain. Then do your analysis, KVL, KCL, Ohm's law. Keep in mind you will have a complex numbers because in phasor domain they will be in complex numbers. Then find the unknown things, the unknown current, voltage, whatever. After that, you need to calculate or convert it back to time domain. So let's do the this question, which is let's find all of the currents, or let's find all of the currents, all of the voltages here in this question. So how to calculate them? The first thing is convert time domain to phasor domain. How to convert this? Basically, look at the start with the sources. So we have one voltage source. So we have 16.97 cosine omega 3 cosine 377t. So basically we will say omega is given indirect way, so omega equal 377. Then in order to find V bar, we can say direct. We don't need to over justify many times, say V max over square root of 2 or other than that. So we will say direct 16.97 over square root of 2, which is V max over the square root of 2. Because we are using the RMS representation. Again, the textbook used the max, while in our analysis we're using the RMS. So in other words, the phasor domain V bar equal to V RMS angle alpha, or in other words, V max over square root of 2 angle alpha. Alpha here, there is no alpha, so the angle will be 0. So this will be 12 angle 0 degrees volts. And of course, we are using the RMS representation, so sometimes we put sub-RMS. It's not necessarily to put it, but just like to follow some procedure. Then, the other thing, we need to convert the other parts of circuit elements. After converting the sources, we need to make sure every other element in this circuit in ohms. So the resistor in ohms, there's all of the resistance in ohms, so there is no need to convert them. While we have a capacitor C1, inductor L1, another capacitor C2. So we need to convert every element. So basically, in order to find ZC1 bar, don't forget to put bars because all of them are complex quantities. According to our analysis, it will be 1 over j omega c, or in other words, negative j times 1 over omega c. Omega is given as 377, given in the question in the time domain expression. Then c, it is 2.65 times 2.65, 10 power negative 3. It's 10 power negative 3 because it's milli, and as we know, milli 10 power negative 3. So the answer will be negative J1 ohms. So what you're going to do, you will put negative J, then substitute in the calculator this expression alone. Then it will be 1. So therefore, it will be negative J1. The other element, which is the second capacitor, ZC2 bar, it is 1 over j omega c2, or in other words, negative j over 1 over omega c, which is going to be negative j divided by 377, and that capacitor is 1 times 1.33, 10 power negative 3. Then again, substitute what's inside the brackets in the calculator, then it will be as 2, so it will be negative j2 ohms. Then the last element, which is the inductor, ZL1, which is j omega L1. Then it's going to be j times 377 times L1. L1 is given as 2.65 times 10 power negative 3. 10 power negative 3 because it's milli. Then just you will substitute inside the brackets. You don't need to substitute j in the calculator to find this because you're doing this as fast as you can. So it will be as, the answer will be 1, so it will be j1 ohm. Okay? That's the first step, which is very important to convert all of the circuit elements from time domain to phasor domain. However, maybe in the textbook, some problems already been converted in phasor domain. Then you don't need to do this the first step. How can I make sure is this circuit in time domain or phasor domain? Look at the units. Whenever you see the inductor in Farad or inductor in Henry, capacitor in Farad, then definitely this is time domain. Whenever you see Vs of t or you see the cosine term, then this is also time domain. While whenever you see any complex numbers for the sources or you see everything in ohms, then this is on phasor domain. Then you don't need to do the first step because it's already been converted. Now, the next step is redrawing the circuit and write the new values that we got. So this is the circuit in phasor domain. So in phasor domain, the source will be 12 angle 0 degrees. Then for this inductor J1 omega, this capacitor negative J1 omega, then the other capacitor is negative J2 omega. And our target is to calculate all of the currents, all of the voltages. So according to the procedure that we know from DC circuit, we can apply it here, which is let's label all of the current directions, all of the voltage polarities. So we will assume a source current going out from the positive part of the source. And don't forget to put bar above this quantity because again we are dealing with complex numbers, it's phasor domain. If you didn't put bar, then it will be similar to DC. It's not DC probably, it's AC. But again, we will make it similar to DC by making the phasor domain. So it's very crucial, very important to put the bar above the symbols. Then this current IS will be splitted. So the first thing, let's assume all of the current directions. So I can say this is I1 bar, this is I2 bar, then the same for this current I3 bar, I4 bar. So we have 5 currents. So we will say that by looking at the circuits, we have 5 essential branches because 5 different currents, 5 essential branches. While we have how many branches? We have 1, 2, 3, 4, 5, 6. We have 6 branches. How can I know like the 6? Because these 2 can be considered one essential branch, just for your information. Anyway, the next step after labeling all of the current directions, let's do the voltage polarities. So the voltage polarities for the resistors or the impedance, they are no longer, we will no longer say resistors, no, let's say impedance, everything in ohms, then in ohms, in AC will be called impedance. So for the first 2 ohms impedance, we will need to make sure ohms law positive, therefore we will not let the arrow enters the positive sign. So this will be VA bar. Then for the 1 ohm plus minus VB bar. Don't forget to put the bars. For the J1 ohms plus minus VC bar. For the negative J1 plus minus VD bar. What else? Negative J2 ohms plus minus VE bar. And what we have 12 volts, this is V source. Okay? Does this make sense? Okay, it's the same as we know before, but just put bars above these quantities. Then, let's do our analysis. So we have the only given information is the source. So start from the source side. When we start from the source side, we have the voltage of the source. Then the current is unknown. How to find the currents? Any thoughts? How can I find the current of the source? Okay, we'll start from the source side because the source is given. Find the equivalent resistance. Then after finding the equivalent resistance, we can calculate the source. So basically, we will say that let's calculate the Z equivalence. So the first simplification that we can say VC and V, or negative J2 and J1, are those series or parallel? What do you think? Parallel. If you are unsure, label the nodes, as we used to do before. How about J1 and 1 ohms? Parallel as well. So those are parallel. So we will say that negative J1 parallel with 1. And we have here J1 parallel with negative J2. So in other words, we can say VC equal to VE because they are in parallel, the elements C and E. And the same thing, VB equals to VD, right? So let's do the parallel. Basically, their multiplication over their sum. So this will be negative J1 times 1 over negative J1 plus 1. So keep in mind, negative J1 and 1 cannot be combined with each other because each one in difference. coordination, so the answer will be 0.5 minus j 0.5. So you need to learn how to put this in the calculator, and finding the answer with less than 30 seconds. If it takes more than 30 seconds, then you need to make sure to check your ability, or to improve your ability in how to use the calculator. Then the other thing, which is j1 parallel with negative j2 equal j1 minus negative j2 over j1 plus negative j2. So this one also you need to do it as fast as you can. We don't want to spend a lot of time on just this product, doing this product or doing this simplification. So please make sure, practice very well in the calculator, because that's the most important thing that you will, or the most difficult thing that you will see in the second exam is basically, I know how to answer, but I don't know how to use the calculator, or the calculator is not functioning well, or I spend too much on the calculator, spend too much time. So that's the challenge on the second exam. Other than that, it's the same. Series, parallel, KVL, KCL, Ohm's law, complex power, so as we will discuss later. So you will realize that we already know these concepts, but the problem is the lack of experience in dealing of complex numbers. So again, please practice very well in the complex numbers. Make sure you're from now, don't wait until the exam week. Make sure from now, please, practice on the complex numbers. If you have any problems, you can see any open sources for how to use the calculator on the internet. If you still have difficulties, feel free to reach me at my office hours, during my office hours. So let's simplify the circuit. After doing this parallel, then the circuit will be like this way. So it is 12 angle 0, 2 ohms. Then the equivalent impedance, I'm going to replace it by a box, the other one by a box. So this impedance is j2 ohms. The other impedance is 0.5 minus j0.5 ohms. Then the only current that we will have in this circuit is IS. So this remains as plus minus, I can write it for the voltages. This is plus minus VA. This is plus minus VB and equal the same as VD, because they are in parallel, and don't forget the bars. This is plus minus VC, which is the same as VE. Again, why? Because all of them are in parallel, and in parallel means sharing the same voltages. Then, how to calculate I source? Either we can find Z equivalents, or you can say it's single loop. So maybe we don't need to find the Z equivalent, we can just say single loop, then I will be V over the sum of the impedances. That's one way. Or if you still want to find the Z equivalent, that's still correct. Any way that you like, all of them are correct. So let's do the analysis. Then we are in single loop. So in single loop, and we have only single source, so therefore I source will be V source over the sum of Z of the resistor impedances. So it will be V source, which is 12 angle 0 degrees, divided by 2 plus 0.5 minus j0.5 plus j2. Again, please make sure to practice in how to find this expression using the calculator, and shouldn't take more than 30 seconds, or I would say 40 seconds at max. So IS will be 4.12 angle negative 30.96 degrees amperes. This is I source. Now I know I source. Since I know I source, I can find all of the voltages by applying Ohm's law. V equal I times Z, I times Z, I times Z. So how to find the currents or the voltages? Let's start with VA. VA bar equal I source times ZA bar, which is going to be as 4.12 angle negative 30.96 degrees times ZA, which is 2. So actually, when you multiply, you can just multiply the magnitudes alone without the angles. So it will be, because 2, there's no angle in it, it will be 8.24 angle negative 30.96 degrees volts. That's VA. Then VB equals to I source times, I would like to name this as Z1 bar, this is Z2 bar. So times Z1 bar. So I source 4.12 angle negative 30.96 degrees times Z1 bar, which is 0.5 minus j0.5. When you do the multiplication using the calculator for every complex number, puts a bracket, then put the multiplication of the product, then put a bracket. So to avoid any some mistakes that you might face, so please, when you insert any complex numbers, put a bracket for every term or every number, then put the multiplication or addition or subtraction, whatever you want. So just make sure to put the brackets. Then the answer will be, using the calculator, 2.91 negative angle, negative 75.96 degrees volts. Then VB again is the same as VD bar, VB bar and VD bar. Then VC bar equals to VE bar, which it will be IS bar times Z2 bar, which is 4.12 angle negative 30.96 degrees times J2. So it will be as 8.24 angle I think 59.04 degrees volts. Okay? You can say volts or volt sub RMS. Both of them, I'm okay with it. Now, we calculated all of the voltages. What's the remaining thing, which is the currents. We know all of the voltages. How to find the currents? You can go back to the original circuits here and say we can find the currents by applying Ohm's law, because V equal I times Z, then I will be V over Z. Okay, let me give you a few seconds to write this, then I will go to finding the currents. Okay, let's go to the circuit, which is the same circuit, which is 12 angle 0 degrees. And this is negative J1. This is J1, negative J2. And the currents, this was I source. This was I1 bar, I2 bar, I3 bar, I4 bar. And regarding to the voltages, we know VA bar, we know VB bar, we know VC bar, and we know VD bar and VD. I think this is VC. This is VD bar. This is VC bar. And the last one, this is VE bar. This is the assumption. I just redraw the circuit. Then we know all of the voltages. So basically, we will use Ohm's law to find the currents. So we can say that I1 bar equals to VB bar divided by Z1 bar. So, or ZB actually. It's called ZB, which is the corresponding resistor. So VB, we already calculated it as 2.91 angle negative 75.96 degrees divided by Z1 bar, which is 1. So I1 will be 2.91 angle negative 75.96 degrees amperes. I2 associated with VD, so it will be VD bar divided by ZD bar. Then VD bar, we know is the same as VB, which is 2.91 angle negative 75.96 degrees divided by J1. Then the answer will be, I think, negative J1 divided by negative J1. So the answer will be 2.91 angle 14.04 degrees amperes. This is I2. How about I3? I3 bar, I3 associated with VC, so it will be VC bar divided by ZC bar, which is going to be VC bar. We calculated it as 24 actually, 8.24, angle 59.04 degrees, divided by ZC bar, which is J1, divided by J1. So the answer will be 8.24 angle negative 30.96 degrees amperes. Then the last one, which is I4, I4 associated with VE, which will make it VE bar divided by ZE bar. Then it's going to be as 8.24 angle 59.04 degrees divided by negative J2. So the answer will be 4.12 angle 149.04 degrees amperes. Okay? Any question? Okay, I encourage you to go to worksheets. I already mentioned last lecture, but I'm going to also mention here. Go to worksheets number 9. If you still didn't discuss or didn't study this, please go there. Read the worksheets. Try to do the example by yourself. Then look at the answers. They are already written in details. Now, also there are some recommended textbook problems. Problems 5.1, 5.6, 5.12, 5.15, 5.20, 5.23, and 5.26. I encourage you to practice those now. Don't wait until the exam week, okay? And as we know, there will be a quiz on Wednesday. The Wednesday quiz will be on chapter 5, which is AC circuit analysis. So this is the end of chapter 5. Then, so the text or the quiz will be solve the AC circuit analysis. Convert time domain to phasor domain, do your analysis KVL, KCL, Ohm's law, then convert it back to time domain if it is needed. Like in the previous example, or this example that we just finished, it was just calculate them in phasor. There is no need to convert them in time domain. But in case, if we need to find the time domain, it will tell you find VS of t or IS of t or something like that. Other than that, the default is to find the in phasor domain and stop there. Okay? Any question about chapter 5? Okay. So this is the end of chapter 5. Let's start chapter 7, which is related to the power. In DC, we discussed first Ohm's law, or how to solve the DC circuit analysis, equivalent resistance, etc. Then we start discussing the power and Tilligen's theorem. Then the same thing that we will do it here. So we already done with the how to do equivalent impedance, how to solve the AC circuit analysis. Now, how to do the power in AC. And the same thing, which is how to do Tilligen's theorem, etc. Then, single phase steady state power, AC power analysis. It's called single phase in purpose. Why? We will discuss something called three phase later, three phase AC. So anyway, you can consider it now as just single phase AC, steady state power, and also steady state power is different than transient. This is also more advanced powers. But anyway, the same manners that we discussed in DC, let's do something similar here in AC. So let's start with the topics called instantaneous power. So as we know in AC, in DC actually we used to say V is constant, I were constants. In AC, V will be V of t, I will be I of t, right? That was in DC and AC. In DC, we used to say the power equal V times I, and the power was constant, right? Then in AC, the power will be V of t times I of t. So do you think the power is constant? No, it's no longer constant. It's a function of time, P of t. This means the power is changing depending on the time, changing of time, function of time. So that's what we will see here. And this is called instantaneous power. Why is it called instantaneous power? Because it's changed at any instance. This is our topic, which is instantaneous power. Again, it's called instantaneous because you can substitute at t equal 1 second at this instant how much the power will be. At the instant of 0.5 seconds, at 1 millisecond, 1 microsecond, whatever, which is changing with time. So this is the time function, which means the power will be as a function of time. There will be a waveform for the power. Now, our concern is how to calculate this, the power. So here, as I said, like instantaneous power, P of t and V of t times I of t. And the same scenario that we used to discuss before about the power absorbed, power supplied, if the power leaving, or if the current leaving the voltage, or the positive part of the voltage polarity, then it's supplied. If the current entering the positive polarity of the voltage, then it's absorbed. So just recall these definitions. Then, we know the generic expression for V of t equals root of 2 V RMS cosine omega. This is the RMS representation. Then, I of t, the same thing, I RMS, root of 2 I RMS cosine omega t plus beta. But we use different angles, alpha and beta, to make sure that the angle of the voltage is not the same as the angle of the currents. Okay? Then let's do the multiplication, because the power equal V times I. So this is V of t, this is I of t. So after we do the multiplication, we can apply some identities, trigonometric identities, like cosine times cosine. Cosine times cosine will be, for example, cosine A times cosine B will be cosine A plus B plus cosine A minus B. So after making simplifications, we end up having this final expression. This is the final expression for the instantaneous power. Then, by looking at this expression, we can realize two things. There are two terms. The first term and the second term. The second term is actually constant. Time independence. There is no time. Why? Because when we subtract them, omega t and omega t cancel each other. Then the second term, it's time dependent, so it's sinusoid. Because it's in cosine. Anything cosine sine waveform could be sinusoid. What the other thing? The other thing that we can realize, we have 2 times omega. So this is called double frequency term, or double frequency term. So again, this sinusoid term is time dependent. Then we realize that the instantaneous power has a constant part and has a part that's changing, sinusoid with time. So most likely, if we say the sinusoid waveform alone, it will be something like this. Constant parts, something like this. Then if we mix them together, what will happen? It will be like this. Something like that. The power. Okay? So again, the complex powers has 2 different components. We have the component that's constant term. We have the double frequency. This is for the instantaneous. Now, there's some things called average power. We have the instantaneous power that's function of time. Now, the average power, the overall idea about the average power is try to find a constant value of the power. So we don't want to say the power is, for example, 200 cosine 377 times 2 omega t plus something like that. So we don't want to say all of this long expression. So there's something like average power. So the average power, basically, we need to find it. So remember, when we used to say about the AC circuit, like voltage or currents, we cannot say there is average voltage or average current because the sinusoid term equal to 0, right? The average of the sinusoid term. Now we need to find the average for the instantaneous power. So let's go back here and see that the sinusoid term average is 0, right? Average of sine or cosine is 0. The constant term average is non-zero. So whenever we do the average power, it will be only the constant term. Constant term of P of t, of the instantaneous power. That's it. So as a result, we will say that P of t equals to the sinusoid term plus average power, P average, or in other words, this is the same as constant term. So again, the average power, we will use it as an indication to be the constant term of the power, which is constant term of the instantaneous power. And it will be V times I times cosine alpha minus beta. So we will see that the average power is similar to the power that's in DC, right? Power in DC, V times I. And here we have V times I. But the thing which is we have cosine alpha minus beta. So alpha is the angle of the voltage. Beta is the angle of the current. In DC, the angle of the voltage was 0. The angle of the current is 0. So cosine of 0 is 1. Therefore, P equal V times I. That's it. Then here, in AC, no, we have angle of voltage, we have angle of current, therefore cosine alpha minus beta. Okay, does this make sense? So far, in time domain, we have two things, two definitions. Instantaneous power, average power, right? That's in time domain. So I would say that, let me write it in different color. Time domain, we have average, or we have instantaneous power. And we have average power. And let's recall the AC circuit in chapter 5. We did the phasor domain, right? So how is the power looks like in phasor domain? So our concern is in phasor domain. How is the power looks like? Okay. In phasor domain, most likely we will use something called complex power. Basically, in time domain, we used to have V of t, I of t. In phasor domain, it will be V bar, I of t will be called I bar. P of t will be P bar. Yes, but we did prefer to use the simple P. We will replace it. Do you remember when I talked about the resistors? We'll replace it by a symbol Z. Then he will replace it by symbols called S. And we will put bar, S bar. So as we know, in DC, P equal V times I. In AC, S bar equals V bar times I bar. That's something looks like. But actually, we will add a slight modification. Not only as V times I, we will add a star above the I. What does star mean? It means conjugates. Complex number conjugates. Recall, what does conjugate mean? Conjugate. If we assume that, for example, I can assume A, or let me write different, like A bar equal 3 minus J4. Therefore, A bar conjugate will be 3 plus J4. Just flip the sign of the imaginary part axis. Or if we have it in polar, like B bar equal 3 angle 30 degrees, then B bar conjugates, you will flip the sign of the angle. So if you have rectangular, you flip the sign of J, or polar, you flip the sign of angle. Yes?
What if you said 60 degrees instead of negative 30?
30 degrees, yeah.
Could you say 60 degrees?
I said 60. Okay, I'm not my bad.
So it's
3 angle 30 degrees. It will be here. Then when you do the conjugates, you will flip the sign. It will be negative 30 degrees. Okay? So whenever you have it in polar, flip the angle. Whenever you have a rectangular, flip the J part, which is the imaginary part, the sign. So again, the star here is in purpose. It is conjugate, means conjugates. Complex conjugates. So as a result, in phasor domain, we will no longer say power, we will say complex power. Now the power in phasor domain is no longer function of time. I'm sorry, it's no longer function of time. Yeah, now it's here complex number. Okay? Then, how to do the analysis by converting this to phasor domain? Basically, okay, so I will say that since we have V times I conjugates, V bar equal V angle alpha, I bar equal I angle beta. Then let's do the products. So V angle alpha, I times I angle beta, then we have a conjugate. So this conjugate means flip the sign, we will make it negative. So here, VI angle beta. Then, according to the procedure, V times I, the products. Then we have alpha minus beta. That's what when we do the products for any constant. Okay? Then convert this phasor to polar, which will make it as V times I angle alpha minus beta, which is VI cosine alpha minus beta, plus J VI sine alpha minus beta, which is just we applied converts from polar to rectangular coordinates. Now we realize by looking at these formulas, we have a time domain. We have rectangular coordinates, we have polar coordinates, right? Rectangular coordinates, it will be real parts, imaginary parts. Real parts we will call it P, imaginary parts we will call it Q. Then we have V times I in polar coordinates, this we'll call it S. Alpha minus beta, we will call it theta. So as a result, we will say that S bar in polar will be S angle theta, which means VI angle alpha minus beta. In rectangular, S bar equals P plus JQ, which means VI cosine alpha minus beta plus J VI sine alpha minus beta. So in other words, now we have two formulas to find the power, or two formulas for the power, formats, for the power, which is rectangular or polar, or we can say also S bar equals V times I conjugates. The way that I like is to use this. S equal V times I conjugate, and that's it. So we will use this. While how about the other formulas, how to find P, how to find the Q, how to find S, how to find theta? It's a complex number. So you know how to convert the complex number to polar. You know how to convert the complex numbers to rectangular coordinates. Then that's it. So if you know how to do this conversion, then problem done. Which is, you don't need to say, to memorize, it's VI angle alpha minus beta or VI cosine, VI sine. You don't need to memorize this. You need to know just V bar times I bar conjugate, and that's it. Then do the conversion. What you need to know is if we say like find P, P is the real parts, Q is the imaginary parts, theta is the angle in polar, S alone without a bar, this is the magnitude in polar formats. That's the thing that you need to know, which is S angle theta or P plus JQ. Other than that, you know how to do the conversion between polar to rectangular and the vice versa, and rectangular to polar. Okay, is this clear? Now, recall how we know if this element is absorbing or supplying. So in DC, we used to say if the current enters the positive, then it's absorbed. If the current enters the negative, then it is supplied. That's what we used to say in DC. Now, in AC, the same thing, but we will say instead of power, we will say S instead of P. So we can say here, S bar absorbed equals to V times I conjugates. Then for the other one, S bar supplied equals to V times I conjugates. Then if we need to calculate absorbed for the first part on the left side, which is S supplying equal to the negative of S absorbing, the same thing as we used to do before. Then for the other thing in the right side, then we can say S absorbed equal to the negative S supplied. Okay? We know this, but here just we apply it in AC. Now, again, the complex powers, again, it is V times I conjugates, and it can be written in polar or rectangular coordinates. We said S, P, Q, and theta. Now let's focus more on the name of those and the units of those, because the units of the power is no longer watts. It can be something different. How? Whenever we do the complex power, the unit that we will use is VA, which is volts ampere. We no longer say watts. Watts only the units of the real parts or of the real power. Then S is called apparent power, and the unit is volt ampere again. Don't say watts, volt ampere. Theta is the angle in the polar coordinates, and we will call it power factor angle. You must memorize all of these definitions. It's a must, okay? Because we will use it a lot from today's lecture until the end of this course. P is the average or real power, and the unit in watts. Q is called reactive or imaginary power, and it's in VAR. Keep in mind, VAR means volt ampere reactive, and must be lower cases for VAR. Other than that, volt ampere alone must be upper cases, watts must be upper cases. The only lower cases is in Q, which is VAR. So as a result, we have real power, imaginary power, or reactive power. Then we have apparent power, power factor angle, complex power. So we have 5 definitions. The relationship between them, this thing is in polar formats, this thing in rectangular coordinate formats. So it's just like formats. The math is easy, but what matters with us is the definition or the meaning of each one. S bar, again, it's volt ampere, the unit in volt ampere, which is the complex power in volt ampere. S alone, without a bar, is the magnitude, or call it apparent power. It's the unit in volt ampere. Again, S alone, without a bar, it's complex. It's not complex number. It's not complex power. It's called apparent power, which is basically the magnitude of the complex power. Then theta is called power factor angle. It's not only angle alone. We call it power factor, and it's been written this in purpose. P is the real power or average power. We will call it real power, and this is the only thing that's in watts. So the power again is no longer in watts, only real power in watts. Then we have Q, reactive power, and the unit is VAR. Keep in mind, VAR must be in lowercase, so volt ampere reactive. Okay? Again, you must memorize this, it's a must. Now, since we have 5 definitions for the power, we are a little bit getting confused. So, okay, complex power, apparent power, average power, reactive power. Okay, so what's actually, what does this mean? What's the meaning of real power? What's the meaning of reactive power? Or overall apparent power? What do I mean by those? So, yeah, we have got many things. Or even like when we pay for the utility, do we pay, since our electrical circuit is AC, not DC, do we pay for real power? Do we pay for reactive power or complex power? What do you think? Recall when you look at the utility bill, the unit is watts, kilowatts hour, right? So we will pay for the net energy that we pay based on real power, not the reactive power. Okay? So we are consuming reactive power, but we will not pay for this. Is this feasible for the utility? It can be feasible for residential loads. While for industrial loads, there is another meter for the reactive power. And they will get the industrial loads, they might get some penalties if they have some bad consumptions of the reactive power. How? We will discuss this, I think, in Friday lecture, how to do this. But here, in today's lecture, which is how, or what's actually the meaning of real power, reactive power, and this power. Look at this chips. Okay. When you buy this bag, it's most likely you will feel like it's filled, right? But when you open it, you will see maybe some chips and something inside the chips keep it fresh. Some air or something inside it, right? To keep it fresh. So try to open this bag. Leave it for a week. Then try to eat it. Is it fresh? It's no longer fresh. Why? There's something filled with it. Keep it fresh. While if the bag is locked, I mean if you didn't open the bag, leave it for a month and try to open it. It's still fresh, right? So there's something inside the bag, keep it fresh. While when you open the bag, what you are actually eating? The chips. You are not eating the same thing that keep it fresh. So you can imagine this. The whole bag of the chips is the apparent power, or say like the complex power. Then what you are actually eating is the real power, the chips. That's what you are eating. This is the useful thing. Then the reactive power, which is after you open it, it will disappear, right? That's how you can imagine this. So you are not actually using or eating the real power, I'm sorry, reactive power, or the material that keeps it fresh. But it's important to have it, right? Without it, the chips will no longer be fresh. Without it, you cannot eat the chips and enjoy the chips, right? So the overall thing, the whole bag is the complex power. Then what you are eating, or the chips, is the real power that's useful for us. Then the reactive power is something that's to keep the chips fresh. Now, the same thing, like if the percentage between the reactive power and the apparent power is high, then there's something wrong. Like what? When you open the bag, so do you think it can be okay when you purchase a bag and you'll see only 2 pieces or 3 pieces of chips, while the other thing is filled with material that keeps it fresh? It's inconvenient for us, inconvenient for the customer. So our target is to make as much as high useful power, as much as high amount of chips, and as much as low of the material that keeps it fresh. And the ratio between them is called power factor. So we will need to make it 90% of the chips is real chips, the chips that I can eat, are close to 90%. Okay, so we will discuss more about the power next lecture. So let's stop here at the chips.